Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 46 and in this lecture we will be studying the process variation in nanosheet FETs. Now outline of the talk will be because of process variations, what are the degrading factors, few of the degrading factors because of process variation. That will be the general scheme for this lecture series. One of them is, first of all, is of course the self heating effect, and then what are the methodologies available to remove or mitigate the techniques of the ill effects of self heating effect. We will also look into RDF, which is random dopant fluctuations, which happens more so at very low technology nodes, the influence of interface trap charges, work function variation and RDF fluctuations, and we will look into each one of them in details as we move ahead. Okay. So, let us look at the process variation in advanced FET. What do you mean by process variation? See, when you are at the design stage, you use these EDA tools to design the devices and TCAD tools to design the devices, and then you use your EDA tools to extract the circuit aspects of those devices. However, when you actually go to fabrication, then whatever you have given in the design flow may not be exactly replicated in the process flow, right, and there will be therefore some process variations available to us. Now, the problem is the process variation especially can be of two types. One is of course the process variation of the device dimensions and also of the doping of the device. So, you wanted to have a device dimension of say 2 nanometer, but when you actually did a lithographic step and you did an active layer deposition, you saw that it becomes 2.5 nanometer or 2.2 nanometer. Now, because of these uncertainties, as a designer you are also supposed to look at the process variation, which means that if you give a nominal device, then this will be the characteristics. If you give a process variation based devices, this will be the characteristics, so that the users are aware a priori about the ill effects of process variations. Now, look at the second point therefore, due to the difficulty in controlling the variations in different fabrication steps such as oxide growth, channel source drain doping implant, photolithography and etching in modern technologies. So, in modern technology the process variations, though they have become very stable, but there is still difficulty in controlling the accurate values of these variations, and more so it has become more and more difficult for low technology nodes as compared to higher technology nodes, and that is the reliability of the device comes under the question. The reliability of the device means the reliability of the device to perform as per the expectation of the designer, that comes under the questions when you do a process variation. One of them is self heating effect which happens. This is nothing to do with per se the process variation, but these are the ill effects of the device itself. Now, you see when we were discussing nanosheet FETs, if you remember correctly, the sheets were running between source and drain, right, and it was surrounded on all the sides by the oxide layer, and it was connected to source and drain. If you look at the figure here on the right hand side, which you see here, if you look at this figure here, this is the sheet which you see, and the sheet is connected between source and drain, right, and there will be a current flowing through the device itself. Now, and this is the substrate, silicon substrate, and then I have this BDI here, a low-K silicon dioxide which connects between source and drain, so that from the low side we do not get any charge carriers. What you see is a thermal diagram, right, which means how the thermal or the heat is getting dissipated or collected within the structure. So, if you see, I will just show it to you. The red ones are basically the hot spots. The reds are basically the hot spots, which means that the red area, which is somewhere here near the drain end, you will see the temperature is around more than 470 Kelvin, which is 473, 474 Kelvin, and the substrate is 328 Kelvin. So, there is a big difference between the temperature on the active region and the passive region of the device, and approximately 100 Kelvin change is there, more than that, in fact more than that change is there. And if you can see carefully, the hot spots are actually on the drain side rather than on the source side, and the reason being, with increased value of the velocity of the charge carriers as they move from source to drain, on the drain side they almost do a velocity saturation, heavy kinetic energy is gained, it strikes with the material particle of the sheet and dissipates its form of heat. However, please understand, there is no way this heat can be dissipated through an external world, because there is no metal layer, there is no external source layer. So, what happens that the heat gets accumulated, right. And therefore, the second point, the transistor will generate heat when they are operating. Operating means when they are operating in the saturation region. Now, this heat will does what? Will degrade the carrier mobility. Degrade the carrier mobility means basically they will try to make the current small. Similarly, with this heating effect, there is an increased problem of electromigration, and the interconnects themselves gets heated up, and they might get the contact between the interconnect and the device might be broken, and the reliability of the device comes under question, and therefore, you will have large failure rates available to you in presence of self heating effect. Now, look at the left hand side figure which you see here. Left hand side figure, if you look carefully here at this particular diagram, then you will see that it gives you the various types of materials: silicon, germanium, silicide material, silicon which is less than 10 nanometer, and then silicon dioxide, the oxide layer, and this shows me the material's thermal conductivity, right. Thermal conductivity basically tells me that with 1 Kelvin change in the temperature, or the change in the temperature, how much amount of power you are actually wasting, and gives you these values of self heating effect. So, what is the meaning of self heating? Self heating is basically meaning that the current flows because of applied potential, because of which there is a large kinetic energy gain, which converts into heat energy. Heat does not get space or even time to get dissipated across, and therefore, a constant generation of heat takes place near the drain end of the device. Now, if we took this device, the left hand side, then as you can see, the red spots are all created near the drain end, right. And typically the temperature is above 365 Kelvin temperature, whereas the yellow ones or the green ones which is coming is 40, which means that approximately 20 to 25 Kelvin temperature gradient is there within the device itself, right. And of course, the most hot spot happens to be typically the second sheet here, because second sheet is sort of insulated from by the top sheet and the bottom sheet. So, the maximum heat which you get will be somewhere in the second sheet, right. Now, whereas the bottom sheet, if you see, which is the channel number 3, has reduced because it gets path for its heats to get dissipated through the substrate, right. Now, if you look at the second figure which is here, and it shows you the lattice temperature TDK in terms of Kelvin, and this is along the dimension of the channel which you see. Then this is the starting of the channel 30 nanometer, and this is the ending of the channel, let us say 45 nanometer, 50 nanometer channel length I am using it, followed by source and drain. And if you plot it, you see obviously the heat or the temperature rises within the channel and not on the source and drain region, right. It is maximum near within the channel itself, and the increase in the value of the heat temperature, lattice temperature, is also maximum for the top and the middle channel. Your bottom channel, if you look very carefully, which is in black color, is having a reduced temperature. Why? Because it gets excessive paths for the heat to get dissipated, whereas if you look at the red and the blue one, it does not get any extra space to dissipate, and therefore, their temperature is higher. Then if you go towards the source and drain region, then you see the temperature again starts to fall as you move towards the metal contact, and that is obvious. there will be therefore a temperature gradient between the drain edge of the channel and the metal contact which is kept here. Similarly, there will be a temperature gradient between the metal contact and at the source end of the channel. Let us see the last figure which plots drain current with respect to gate voltage, and the black one is with self heating and the red one is without self heating, and you will see that this is for VDS equals to 0.5, this is for 0.7. I have not shown here the black one here, but it is actually one over the other. So, at very low values of VDS, the self heating effect does not make a sense. It's almost non-existence in real sense of it, right. And the reason being that such a low volt potential is there, the current is so small that you cannot distinguish. But when you increase your VDS to 0.7 volts, which is this one, then you can see that your decrement in the value of your drain current with self heating effect is there, and this decrement is primarily because of the reduced mobility which happens due to larger scattering near the drain end, right. So, what we have seen is through our study, and the paper is available to us, and that is this paper which we have referred to, our group's paper, and this is what we have found out. And the reduction is approximately 6% when we talk about reduction in the drain current, right, with respect to the VDS equals to 0.5. With at VDS equals to 0.005, there is no change obviously in the current. Now, let us look at some self heating effect mitigation techniques. One is very simple, use a high conductive material, right. Because of its higher conductivity, the heat flux will get obviously shifted towards the device substrate, and from where the channel regions you can reduce the value of the self heating effect. So, one good methodology which people have followed is use new high conductive material there. Another concept is that lower the KTH, right, have a device engineering and reduce the value of the thermal conductivity in the active region and will reduce the hot spots. On the right hand side, if you see, I have plotted TD, which is the dielectric current versus KTH, and as the KTH value goes on increasing, the temperature actually falls down because it gets space to remove the heat very fast, right. Similarly, heat flow can happen by two ways or two methodologies. One is through BEOL, which is back end of the line, and another is from the substrate. So, this is from the substrate which you see, and this is from the back end of the line which you see. Back end of the line means from the back side of the device it can actually get dissipated, and from the substrate basically mean the substrate is below the device and therefore, it can dissipate from there. Another methodology which we do is that to increase the contact area. When you make the contact area larger, you allow more and more the heat component to move through, that makes your life relatively easier, right. Similarly, another methodology is a structural modification which people have done, that they have made the source and drain tapered source and drain. So, rather than having this straight source and drain, they taper it out like this. When they taper it, as you can see, the red spots are gone at this particular point. The red spots was 386 degrees centigrade, and they have substantially come down to around 360 to 670 Kelvin by just making it tapered source and drain, right. Why is it so? Because when you make it tapered, then as you move outwardly from the domain, from the channel towards the domain, the cross sectional area increases, and therefore, you get a better way to dissipate the heat away, and that makes it easier to handle. So, this is another solution which people have followed. Another solution is a material based solution, that you use a hetero interface material, and this will actually allow the heat to pass through and will result in a much lower temperature. Now, the drain interface contact resistance obviously has the higher temperature, because it is in the drain side. On the drain side, since you have velocity saturation and more transfer from potential to kinetic, you will have much larger temperature available there, right. However, therefore, a good amount of research is also going on what type of contact material can be used, which can be used to reduce the value of the self heating effect. If you look at this graph which is kept here, then you will see that this red colored is basically the maximum drain current, and the black one is the maximum temperature of the lattice. On the x axis is basically my resistance of the drain, source and gate. And as you can see here, this rectangle is basically for the source, then for the circle you have the gate, and for the triangle you do have the drain part. And we have chosen the value of VGS and VDS to be equals to 0.7 volts. And as you can see here, the maximum drain current is when you try to make maximum drain current. So, first of all, let us see what happens. If I increase the value of RTH, the lattice temperature starts to increase. You see, the lattice temperature starts to increase. Expected also, because when your thermal resistance goes high, obviously the temperature will also go high. But interestingly, what we are looking into the fact is that for the same value of the thermal resistance, if your thermal resistance of the drain is much higher, then I get a much larger change in the drain in the lattice temperature. And this is because of the fact that since the whole phenomena is actually taking place on the drain end more appropriately, we need to find ways and techniques of removing this heat from the drain side at the very first instance. Let me come to the process variability issues. One is the, as I discussed with you earlier, RDA for the random dopant fluctuation, work function variability. We have already seen that ambient temperature is of course a very key factor when we discuss the reliability of the device and the aging of the device. The last part is basically stress and strain, right. Now, if there are large stress and strain available within the device, the reliability of the device also goes down. So, the left hand side is basically how you find out the interface traps, and on the right hand side we have metal grain boundaries, granularity is being present. Now, as you can see here on the left hand side, because of this presence of RTI, you do have these brown spots available, and this is what I was talking about, the process variation, that because of some variation in the process, it cannot stabilize the material there or the circuit there, and as a result the temperature actually goes high suddenly at a particular point. Let us look at the impact of interface trap concentration, and as you can see on the left hand side, as the trap concentration goes on increasing, as you go on increasing the trap concentration, the drain current actually starts to fall down, because the traps actually capture the electrons very easily, right. So, increasing the accepted trap concentration will increase the threshold, and reduction in the value of I off there will be there, and therefore, ion to I off ratio will increase, right. There will be also an increase in the leakage current, provided you increase the interface trap charges density, and that is all visible in all the graphs which you see here, the 4 graphs which you see here. As an example, let us look at the last graph, which plots NIT, interface trap charge concentration with respect to I off and ion by I off ratio, right. So, the black color is I off and this is ion by I off. Now, what happens is that as the trap value goes on increasing, the ion by I off ratio starts to fall down, because of the reason that I off starts to increase in a particular region, and therefore, the leakage current increases. We will look at the impact of the work function variation, right. Now, as can be seen that if you plot ion versus log of I off, it is centered around particular domain, the ion value, right, for various grain size, and that is quite interesting, that even if your grain size varies from 5 nanometer to 30 nanometer, right, we still have a region of interest where the current is available to us. So, for a fixed gate area, as the grain size increases, the work function probability distribution across the gate surface increases, right, and therefore, reduce the number of gains, and this shows a strong correlation between ion and I off is obtained for a higher gate, right, gate grain size. Now, as the TA value goes on increasing, the lattice temperature linearly increases and decreases the thermal conductivity of the gate material. So, as the temperature goes on increasing linearly, the thermal conductivity of the gate material starts to go down, and therefore, a reduced grain size will slightly decrease threshold voltage. When it reduces, this will, now these all are shown again in this graph much better manner. Now, let us come to the random dopant fluctuation. All of you are aware of that if you follow Dennard's scaling law in a much better manner, you will see that the problem of RDF still remains there, the random dopant fluctuation, right, that still remains there. And so, even adding one dopant species there will be heavy fluctuations there. Now, the statistical threshold voltage variation of saturation and linear region is approximately 2.1 millivolts and 3.2 millivolts. Now, this shows a lesser variation in the value of the threshold voltage for higher VDS, which means that when you make your VDS much larger, the effect of RDF is reduced, right, and that is because you have reduced charge scattering, because the electric fields are relatively very large, and therefore, there is a good correlation between I on and I off. Now, that can be seen between in the last figure which you see here, this figure. You see when log of I off, right, and this is I on, and when your rho is equal to 0.72, the correlation factor is quite high, whereas the correlation factor is very low here. That means, when you increase the value of VDS, the correlation becomes very high, which means that I on and I off are almost, there is good correlation between the two. Now, let us come to the analog perspective of nanosheet FETs. We will look into the analog performance, we will look into the multi-stack nanowire, and then contact over active area gate layout. What we did was, and this is quite interesting, that when we tried to make the gate voltage lower and lower, the transconductance actually increases due to the band gap decrease with temperature rise. Now, when you lower your VGS, temperature rise takes place, because of which GM increases because of the band gap decrement. Now, the GM peak decreases due to degradation of carrier mobility height VGS. Now, if you look at the GM versus VGS graph here, then as the value of the TA, the effective temperature goes on increasing, the value of your transconductance actually starts to fall down, which means that the amplification which can be available to an analog device, which is GM times transconductance times RD, which is the drain resistance in the external force, will actually reduce. Now, this ZTC point is a zero transition point below which the reversal takes place. Now, the performance of analog or RF actually decreases as temperature increases, and so for higher temperature, the analog performance is much lowered in this case. Now, if you look at the second graph here, it plots the total gate capacitance versus temperature. So, at 250, for example, if you take Kelvin temperature, difference between the with self heating and without self heating is 5.7, right, and as you go on increasing the temperature, the difference goes on decreasing, which means that at very relatively high values of ambient, the difference between the with self heating and without self heating actually starts to reduce, and makes sense also. However, quite interestingly, if you see the increase in value of your without self heating, the value of CGG increases much larger in this case, right, and that makes life difficult for analog designers relatively at low temperatures in a sense. Now, this is a multi-stacked nanowire for analog performance, and what we have done is that multi-stack, you can see, is I have this gate. So I have multiple sources here. So you have one source, you have one source, two source, three source, and then you have got one gate, two gate, and three gate, and there is another two drain. So it is basically a fingered sort of layered in a multi-stack nanowire, right, and there are horizontal fins, and there are 4 number of fins available to us, 1, 2, 3, 4, and these 4 number of fins is meant to increase the drive current. The structural effect of nanosheet versus nanowire, if you look for the same amount of gate contact, both layout and same, we use both NS and NW. NS nanosheet, NW is the nanowire. Now, since there are 4 sort of fingers available, you end up having large amount of current improvement here. This is basically a 6/10 lateral stacking of the device. So, basically multi-stack nanowire is shown here. Now, the problem is, however, that as you make the area layout change, your parasitic capacitances also change in that manner because of the non-planarity of the structure. So, nanowires have typically 1.1 times or 110% more FT as compared to nanosheet FETs. Now, the smaller effective channel width of the stacked nanowire than stacked nanosheets, right, leads to smaller intrinsic capacitances, right, and therefore, the smaller values of CGG. The CGG gets smaller in case of nanosheet FETs, right, as compared to nanowires. Now, however, the nanosheet FETs, we have assumed it to be rectangular in nature. In reality they will be rounding, and this rounding will result in a decrement in the electric field, which will reduce in the decrement in the value of GM by approximately 10%. When this happens, you typically have much slightly smaller value of GM, and therefore your AV is reduced, the voltage gain is reduced. The FT is given by GM upon 2 pi CGG, and that is quite interesting, that how GM and CGG varies with most of the operations is what you need to study. Similarly, nanowires have approximately 1.5 times larger F max compared to nanosheet FETs, and that is primarily because an increased value of GD drain conductance and an increased value of CGD, which is caused by the effective decrease in the value of effective width, right. And these figures are all available in this research paper, which is quoted here. Similarly, if you look at the F max value with respect to the various values here, you can see that when you do a nanowire sheet in both the cases and nanosheet FETs, F max is much larger in case of nanowires as compared to nanosheet FETs. However, nanosheet FETs are better in terms of CGD and GD as compared to your nanowires. So, as a designer, you need to do a trade off between these two structures in order to understand the structure. Let me explain to you the FT versus the number of floors which you will get. So, there will be also a lateral spacing, remember this I discussed with you when I was discussing here. So, there will be a lateral spacing here, you see, and we were to design the 6, they can be 6 to 8 lateral spaced devices one after the other like this, they are kept like this. And as you can see here, this lateral spacing I am showing you here, right. This is 1 sheet, 2 sheet, 3 sheet, this is lateral spacing. Now, what we have shown is that as you make the number of lateral spacing larger and larger, the value of FT goes on increasing, and it goes up to around 450 to 500 gigahertz. And the nanowire is much larger and nanosheet is relatively smaller. Similarly, if you plot F max versus the number of stacked floor, then also there is a relatively larger increase in the value of nanowire with respect to nanosheets. And this is primarily to do with GD and GM increase in the value of your of approximately 3.3 to 2.4 times. Now, F max then starts to degrade for larger number of floor, and the reason is you have an increment in the larger number of CGD and GD, right, and that becomes a problem with you in the design stage. Let us look at the last part of our discussion on analog design, and this is contact over area gate design. This is basically, if you do for power amplification purposes, the transistor array needs to have a larger number of lateral stacks. I hope you understand why, because you want the output power to be very high. So, what you do, you make the lateral stacking, 6 lateral stacks are there, and there are 4 vertical stacks available too. So, there are 4 floors, 1, 2, 3, 4 floors, and we say there are 6 stacks. So, there are total 24 sort of sheets available to us, right, and these 24 sheets primarily run the current, and higher power amplifications can happen if you do larger number of sheets in this case. Now, you can improve the F max for larger transistor array, but designing this and keeping it reliably designed under process variation is the challenge as far as contact over active area transistor layout is concerned using the nanosheet FETs. Let me recapitulate what we learned for the last lecture. We learned about the basic idea about the process variation, right. We looked into after looking into process variation, we looked into NS FET, right, and then we had comprehensive study or analysis of difference between NS FET and nanowire FETs, right. Then we went for self-heating effect SHE, and how SHE is a degrading phenomena that we looked into the fact, and what are the various therefore mitigation techniques available to remove these ill effects of self-heating effect. Finally, we went into the analog perspective and saw some of the analog figure of merits which can be improved when we use nanowire with respect to nanosheet, and what was the primary reason was to do with GM and CGG change with respect to the variations in the value of the structural parameters. With this we have almost finished the concept of nanosheet FETs. We will meet next time, we will do some other device into consideration. Thank you.